All right, so chapter 6 is on wireless networking. So as it says here, we're going to look at various types of wireless. We will sort of, I think most of the lesson is about Wi-Fi, but there's some other things there, like Internet of Things we talk a little bit about. And you can see, as you see, Wi-Fi features pretty strong in this lesson. Secure troubleshooted Wi-Fi. So when we say wireless LANs, using radio frequency. So basically, we have this spectrum of the electromagnetic spectrum, which basically goes from very low wave, long wavelength, low energy waves, up to very short wavelength, very high energy waves. The higher the frequency, the higher the energy. And that's important to us because high frequency, high energy can be destructive, but it also can carry a lot more data. So we have this thing that we sort of have to balance. You will see a little spectrum with some reference to that as it affects our wireless. But basically, I'm sure you've heard of these numbers like 2.4 gigahertz and 5 gigahertz when you're talking about your Wi-Fi connections. So we do have a range which has been set aside by government bodies, basically saying that you're licensed to use this particular part of what we call the radio frequency spectrum to do different things. And so all of the things that we'll be talking about today will be that radio frequency, a particular part of the spectrum set aside and used for that particular use. Now it mentions here the atmosphere. I'm not sure why they mention the atmosphere, because radio waves do not require any medium. They go quite nicely in a vacuum, but they will travel through the air quite nicely. But they probably travel through a vacuum even better. All right, so this is the spectrum that I was referring to, or this is a part of the spectrum. So this is only the wireless spectrum. The electromagnetic spectrum is much broader, but the wireless spectrum we see is basically working from 100 kilohertz up to 300 gigahertz. So quite a broad spectrum there. Now, I think that, so here we've got our radio. That's our AM radio and our FM radio. So I don't know if anybody nowadays listens to radio, but if you did, you might be familiar with some of the frequencies here, like I'm listening to something that would be in this frequency. And you can see that that's a lower frequency than what we've got here for our Wi-Fi. And there's a bunch of other things like Bluetooth, Zigbee, and RFID. They're all in around the 2.4, 2.5 gigahertz, but also Wi-Fi is also being broadcast at 5 gigahertz. Now, if you get, as I was saying before, if you get a higher frequency, you're getting more energy, more data. And so people like to have really fast Wi-Fi. And so they're going to, they're going to want to have their 5 gigahertz. It will be more dangerous, but we're not really up in the microwave range there too much, I don't think. But some people do sort of highlight the danger of electromagnetic waves when we get to higher frequencies. All right, so we need to use a bunch of technologies to make this work and be stable for us. How are we going to get the electromagnetic waves from one point to another and be stable, and so that we have a secure and a good connection? And so a bunch of technologies have been developed. One of them is frequency hopping. The idea of frequency hopping is within a range. So you could say between 2.4 and 2.6 gigahertz or whatever, the transmitter will move from one frequency to another within that range. So the idea there being that we avoid some of the problems by spreading the risk a bit. Then the other one is direct sequence spread spectrum. that works kind of by just having a really broad, you cover an entire range with the single transmission. So it's kind of, we're also spreading the risk, but we're just sending a lot more. We're sending it over a broader range. Rather than jumping from one to another, we actually just cover them all at once with the direct sequence spread spectrum. And as you can see, around the 2.4 gigahertz range, Wi-Fi is using DSS. Bluetooth is doing the frequency hopping. So from one signal to another. Zigbee using DSSS. Now, ANT it refers to, that's not really widely used, but as it says, it can, that's a good thing I got it on here because I don't have it on my screen. There it is. ANT is a very sort of narrow technology. It's used by Garmin. Now, I have a Garmin watch, and I don't know about any ANT because I paired this with my phone, and so that was Bluetooth because my phone is not Garmin, right? But if I had a Garmin phone, I suppose I could use ANT to do the pairing. All right, so what else? What do we got here? So the point that it's making here is that our devices, our Wi-Fi devices, they're going to be connected to our network by an Ethernet cable probably, and they're going to be powered by electricity, and then they produce a radio wave. And as I said, the radio wave is it'll propagate through anything. It propagates better through air than it does through water or wood or other things like that. And so it'll go further without breaking down its characteristics. So the two devices here could be sending and receiving between each other. Our antennas can work that way, to receive a signal and also to send a signal. Okay, so this is just talking about the direction of the signal. Basically, the signal generally is just going to come out in every direction from the antenna that's sending it. But you can organize it so that the antenna sort of sends in a single direction. They certainly do that with microwave, but we're talking about Wi-Fi here. And I'm just looking up in the top of the room here if I can see an access point. Yeah, there we go. So throughout the college here, we have a lot of different access points. If you came up here and had a look at that at some point, you see it says Cisco. That'd be a Wi-Fi access point. We have some huge ones on the outside of the building, though. I don't know if you've seen those, and that means that you can pick up the college Wi-Fi while you're sitting in the car park or sitting outside in, having your lunch in the winter. So yeah. So those antennae, they could be sending in all directions, or they could be directional, so that they actually have a bias towards a particular direction. So unidirectional, that's what we mean by that. And omnidirectional can go in many different directions, but can be directed. And a range. So we use this term propagation just to mean, how do we actually generate the waves? Line of sight, that definitely does work for some of our transmissions. That's the limiting factor for infrared and also for microwave. But if you have a line of sight transmission, then that means that you can't transmit over the horizon. Now, Wi-Fi is only short distances anyways, but I mean, I was talking about that because it's used for microwaves. Okay, so the point that's being made here is that the signal is going to be propagated, it's going to be sent, but then it's going to have some challenges, I guess you could say, for the signal in actually reaching the devices that want to connect to it. So if there's obstacles in the way, and you'd know this, so we've got our Wi-Fi access point here, because there might be one out in the hall, but we've got a lot of obstacles between here in the hall, right? Because of the doors and the walls, and if there's metal, that's worse. I don't know if you're familiar with this concept of a Faraday cage. Have you ever heard of that? So basically, what we know is if you take a metal wires, and you make a box of metal wires, and then you put a device inside the box of metal wires. We call that a Faraday cage. Then radio signals will not come in and out of that in the way that that they normally would through other things. So we can have a Faraday cage if we had a lot of concrete with rebar in it. I don't know if you know what rebar is, but in order to make concrete buildings stand up and not fall down, is they have to embed into the middle of the concrete. They need to put a lot of metal. And so the concrete holds onto the metal, it doesn't fall down. So that it causes interference to any signal. And it's not complete interference, but it's enough. Now you can design a Faraday cage so that signals won't get in and out. But whenever there's metal around, it's going to interfere with your signals. So how is it going to interfere with them? Well, as it says, okay, so you got these three different things that it says here. Fading, the signal runs into the energy is taken out of it. So that's the important point there with fading, is you lose some energy. Attenuation, that's where the signal loses its shape. Okay, and so that's very important with digital communications, because we rely on what we call a square wave. Square wave is either on or off. And so that can be fixed. Attenuation can be fixed with repeaters. That would also fix fading, of course. And then there's interference, where you could have noise. That is where if there's something else that's generating some other kind of electromagnetic wave that can interfere with your wave. So those are all problems that are faced by your Wi-Fi signals. Refraction. Generally, we use the word refraction talking about light, don't we? Basically, when light travels through medium of different density, then the the actual light generally travels in straight lines, but it will bend if it goes through media of different density. So light is an electromagnetic. Light has two characteristics according to the quantum theory. The two characteristics of light are that it has a particle characteristic, which we call a photon, but the other characteristic it has is as a wave. And so wave characteristics, that's electromagnetic spectrum. So light is on the electromagnetic spectrum. And so if it's refracting, I suppose you could draw from that and generalize to that other electromagnetic waves could be refracting as well. In other words, bending when they go through different media. Reflection. Okay, so sometimes light reflects. So could another electromagnetic wave. Not the same, because it's not going to be exactly the same. You're not going to hold up a mirror to your Wi-Fi and it's going to reflect in the same way light does, because of the differences of the wavelengths, right? What it will take to reflect your particular wavelength will be something of a characteristic that matches that wave size. All right, and so all the different wave size. So what I'm saying by that is what reflects your normal light might not reflect a Wi-Fi. It might, but it might not. Scattering. So your spectra could be scattered, as it says, in different directions. Diffraction. Diffraction, the idea of that is that you have a wave and then it splits into waves that are made up of different wavelengths than the one that you started with. And so what you see here is trying to represent that. Here we have our access point, and the access point is propagating radio waves in all directions. Now, some of those radio waves are being scattered by hitting something with an a very unusual shape. So you can't, you know, a plant has got all kinds of surfaces. And so that's going to scatter the waves in all different directions. We got some diffraction going on where the waves, which were of one characteristic, are actually changed in characteristic when they strike a particular object. You got some reflection going on. Yeah. So the point that it's trying to make here is that this signal is going in many directions. It's actually going out in all directions. That's good because, you know, we got this guy over here who wants to receive that signal. Some of that signal is being reflected. That's good because they were able to get the signal. It's bad because we're getting some of this diffraction going on. And so that's actually messing up the signal. So it's not the original signal that was sent out, and the diffraction has actually altered it. I think you've probably heard of IoT, the Internet of Things. The idea being that you can have some kind of device which either transmits or receives or does both, that is so small that it can be attached to all kinds of mundane and normal sort of objects, so that your clothing in the clothing store or many objects around your house could have an IP address and could be used as some kind of a sensor or some kind of a to act in a certain way when it receives a particular signal. So when I talk about the clothes in the clothes store or the Amazon shop, you know what I mean? The idea of the Amazon shop, people go in and out of the Amazon shop, and they don't need to have their wallet with them. I think they just need to have their phone or something. And so the idea there is that all of the objects in the shop have some kind of a device on them, which would be this Internet of Things thing, where they will communicate with your phone. And so as you go out, the thing you are recognized, the object is recognized, and you're charged for it when you leave. So the personal monitoring devices. So I mean, most of us have got one of those, right? I've got mine here. This is a Garmin watch. I use it because I don't know why I use it. I ride in the desert with a bunch of people, and it's great for races because you can put lap times on it. So you can sort of set out a track. You can say, okay, I'm gonna ride around this, and so I'll start my lap. But to be honest, I don't do that very much. Mostly when I go riding, I just go and just ride. I don't really measure the lap time, but I could. But the other thing that it does, what I actually use it most for, is I look in the morning on my, so I have it paired with my phone. So there's an app that works with it, and it tells me, you know, how much sleep I got, how much stress I had, how many steps I took, how many stairs did I go up, how many calories did I use, you know. So I mean, it's kind of a health thing. So I mean, a lot of people have those. Anything else? Well, it tells me where I've been, so I can that comes even if I don't have my phone with me, but I always do. I mean, if you have your phone with you, you got Google going, right? And then Google knows where you've been, so you can draw a map of where you've been. But even if I didn't have my phone with me, this is taking a map of where I've been. So I mean, you know, I don't know, maybe that's kind of cool. Now the point that I should be making here on the personal monitoring device, it tells me my heartbeat. So I mean, if I had my glasses on, I could see my heartbeat right now. Yeah, 86. And then it measures the heartbeat over time and tells you the low heartbeat that you had. So I mean, it's kind of a stress indicator, right? So I think it's kind of cool. And that's one personal monitoring device. There's many others. Smart homes. Yeah, okay, so you can have all kinds of devices on your fridge, on your doors, security cameras, home area network. So it allows you to have all kinds of devices. Yeah, it's sort of simple things going on. I mean, I don't know, most of you probably got an internet TV or something like that, right? So you can organize it with the Wi-Fi around your house, and then you can sort of watch your Netflix on your TV. It's, yeah. Not just Netflix, you watch YouTube, right? So a wireless personal area network is a sort of an extension of that idea. So the idea is to bring health to people over a distance. So if you had somebody that had to stay home and they couldn't be visited, it costs a lot of money to send nurses and doctors around to visit people. So you could have somebody with devices like that and maybe some other devices that would then connect through a network that a doctor would get an alert if this person had something happen to them that that was dangerous. Yeah, actually, there's people who have watches that will do that. If you have an accident, if you're driving in your car, or if you fell off your motorcycle or something like that, then the police will be alerted immediately, even though you didn't make the call. Just, yeah. And of course, some of these new cars have all of that stuff too. Okay, let's talk about this. So Zigbee has its own standard. And so that's, as it says there, it's used as for sensors. Now, if we're just going to use something for sensors, we're probably not going to be needing to pass too much data. And therefore, we're not going to need to have too much sort of the speed, sorry, not the speed, the speed's all the same, speed of light, right? But the actual data bandwidth, it doesn't need to be too great. And so we can use a lower frequency. And so Zigbee's a standard for that, used for sensors of all different types. And yes, so for IoT devices typically are not going to have, they're not going to be sending a lot of data. Z-Wave for smartphone, sort of similar kind of thing. But what it's doing is it's used for controlling different devices. Yeah. And so it has a distance of about 100 meters, if you're interested in that. I don't know. To be honest, I don't know if we'll ever talk about Z-Wave again. It's a smart home protocol. The type of thing that you can sort of come in and sort of talk to your phone and it turns on the lights and stuff like that. Or maybe talk to the... So Bluetooth, so that's been around for a while. We've all got Bluetooth, right? I mean, if you use earbuds, or if you have a watch like mine that communicates with your phone, or it was a safety feature when back, 10 years ago, 15 years ago, you would have a Bluetooth connection to your radio in your car, so that and a microphone, so that you didn't have to you didn't have to pick up you could talk on your phone without touching your phone. We've got that in one of our cars. I bought a car here. I actually bought it from Toyota, and that was a requirement. So that was back in 2007. Still have that car, but it has Bluetooth. Toyota wouldn't sell you the car unless you bought the Bluetooth. So at that point, that was a safety feature that's how it was explained to me. It was a safety feature so that I wouldn't hold on to my phone while I was driving. I never do that anyways. But yeah, so you could just talk without touching it. So what we know about Bluetooth devices is, yes, they need to be paired. It does have a limited range. It's only like 10, 15 meters in practicality. Somebody will tell you it'll go longer. Yeah, as long as there's nothing in the way. But even with that limited range, you can get some people can hack it a bit. I do remember in our car driving along, and we were using the phone sort of thing with the Bluetooth, and we're picking up somebody else's thing because they drove near to us, right? So yeah, that's not so great. All right, so but people could send you messages on Bluetooth that you didn't want, or they could download from you. That would be bad. All right, so let's look at the Bluetooth here. Low power output for less data. Okay, so if we want, most of the Bluetooth was working in this 2.5 megawatts range. And that's where our mobile devices, if we wanted to use Bluetooth for industrial purposes, we'd use a lot more power. There is another class for Bluetooth, and but it's not really used very much. So ANT, I mentioned before that, and I was surprised when I came across this because this is a Garmin-owned technology, and I have a Garmin, but I'm pretty sure that I'm not using ANT. The reason why is because it's Garmin-owned, it would be, I'd have to have another Garmin device to communicate with, right? And I'm not. I'm communicating from this to my phone. So that's using Bluetooth. So Garmin, no doubt, has some reason that they want to use that. Their own proprietary sort of network. All right. Now, RFID, on the other hand, that's been around for a while and quite useful. I don't know if, so we're going to have toll here in Qatar soon. I know because I've seen the toll gates go up, but nobody's ever said anything yet so far about how it's going to be used. But in Dubai, 20 years ago, they set up toll using RFID. So how the RFID worked in Dubai is you got the sticker that you put on your car, and it's got an RFID chip in it. And so what happens is you go through the toll gate beams beams a signal at your RFID and gets a signal back, and immediately you get charged for that toll. So RFID can be used in that way. And as it says here, there's 3 different ways that you can use it. So the RFID tag can be passive. So it's just waiting for the signal to come. And when the signal comes, that activates it and it sends something back. That would be the passive, passive tag, active reader passive tag. That would be your toll thing, right? It could be the other way. You could have a tag which is actually emitting something, and then the reader is passive, and then when it receives the signal, it sends something back. And you can have them that they're absolutely always active. As it says there, it's commonly used for inventory management. You can put an RFID tag on your clothes in your clothes store, and it'll sort of beep if somebody tries to take them out. Or you could use it to do for payments as well. NFC, so we can have some kind of chip that allows us to have access to things, kind of in the way that these ones work, I suppose. But you can put these tags there, and there is some electricity sort of required on that. Something has to be connected, but it can take it from your phone or whatever. But those tags can be used on gates to allow access, etc. Wireless USB, I suppose we've all got kind of one of those, right? So it's an ultra-wide WAN bit platform. Talks about 2 different types of radio waves on the mouse, right? So one, you've got the radio wave that's going from the USB connector. This is a little radio, and it's connecting to the mouse, right? And so the mouse and this are setting up a little communication using this UWB ultra wide. The other radio waves it's talking about is the infrared. So the infrared, what's happening, if you looked at the bottom of the mouse, you'd see there's a little red thing, or we can see the red, right? And that's sending a signal and then getting the bounce back. And from the bounce back, it can know what movement has been made. And so that's the control that you've got in the mouse. So that's infrared. Infrared is pretty close to the color red, which is why we call it infrared. And yeah, so it's used in that. What else is it used for? You can use it for measuring levels of liquid. It can be used to transmit data. But we can use it for proximity, but checking level of liquid. So that would require that you have a straight line. All right, so that's a straight line propagation and receiving back. That's the only way you're going to be able to measure levels, I think. measure. Oh yeah. So again on my watch, right? When I look at my watch, I see that it's got these, there's something going on there, right? You see, I don't know if you can see the little, looks mostly, no, it's, yeah, it looks kind of green to me, but that's actually that's how it's picking up. I'm pretty sure that's how it's picking up the signal. That's how it's picking up my heartbeat. All right. So, I mean, when you say my heartbeat, what do I mean by that? It's able to determine the blood flow at just below the surface. As it mentioned here, variations in reflection of the skin caused by variations in blood flow. So there's signal going and being sent out by the device, and then the reflection back to it. From that, it's able to sort of get that idea. All right, the remote control on your devices, they're usually infrared, and they work in a straight line, as you know, because of if your furniture's in the way, it doesn't work. All right, so the next bits are about our OSI level, and we talk about the layers 1 and 2, and the MAC part of layer 2. I don't know. I think I might stop at this point, and we'll sort of carry on with this in the next lecture, if that's all right. Let me see. Yeah, we're not even half through. Almost half through. How many slides? 68. You guys okay if I stop now? Yeah, I think that's been a lot of talking. So let's stop there and let's look at what we can do with the